So we'll start in a few minutes. Uh, Around 6:03 we'll start. Yeah.
Okay, sir.
Okay. So we'll get started. Uh, just a second. Yeah. Okay. So hi everyone. This is Arpit. I'm a student at ISC, PhD student at ISC, and your TA for the course Introduction to Biostatistics. And today we'll be talking about lectures covered in week 5, and we'll do some practice questions based on that. Before that, here are some important links. So the first one is the link for the live session, which we are in. The second one is the link for the YouTube channel, where all the recordings of the live sessions are being updated. So the last one I have not yet updated. I'll update the last one and this one together. Uh, Next, we have the Google Drive, where all the materials for the live session are uploaded. I think I uploaded the materials for last week also, but yeah, today also I'll upload if I have not. Yeah. So before we get started, does anyone have any questions or doubts? Okay. So today we were mostly like this week, we mostly talked about distributions, different kinds of distributions, and mostly getting at their expected value, their variance, and how we can use them to solve questions. So in brief, I'll just write down all the formulas and just recap all the distributions so that it's easier for us to do the questions. So the uh, first distribution that we just a second. Yeah. So the First distribution that we talked about was the binomial distribution. So the binomial distribution we talk about when we basically have n number of trials, right? For example, we are tossing a coin n times or we are throwing a dice n times. So we have n number of trials and each of those trials are independent. Right. So basically, when we toss a coin, so the probability of getting heads in the first toss does not really affect the probability of getting heads on the second toss. Right. So the trials or the tosses that we have in this case are independent of each other. So when we have n number of trials and we basically all these trials are basically independent, and when basically, so since it's a binomial distribution, we are talking about two values. So basically, the each of the trials that we have has exactly two outcomes. And so we call them in general success and failure. Right. So if you are interested in looking at the number of heads in 10 tosses of a coin, so the probability of getting heads in a given toss would be the probability of would be outcome. So basically getting a head in a given toss would be a successful outcome and getting a tails would be a failure. Right. So across each of these trials, we have a probability of success, which is denoted generally by P, and we have a probability of failure, which is denoted by Q. And since we only have two outcomes, so Q will be 1 minus P because probability of all of them should add up to 1, right? And yeah, so the main thing is the probability P here, the probability of success in each trial does not change across trials, right? So the trials are independent and the probability does not change across trials. So when we have situations like this, so for example, when we are looking at n coin tosses or n rolls of a die, we are basically talking about a binomial distribution. And for a binomial distribution, here are some formulas that is better if we kind of remember it, right? Because in the exams, we'll have questions based on it. So probability of x equal to k. So x here is our binomial random variable, and k is basically the number of successes, right? So this here gives us what is the probability of getting k successes in n independent trials, right? So the formula is basically nck into p raised to the power k into q raised to the power n minus k, where basically k is equal to 0, 1, 2. So k can vary from 0 to n, and k is always less than n, right? Less than equal to n. Now, if we look at the cumulative distribution function, so which we denote in general as f of x. So f of x, this gives us basically the probability that x is less than equal to k, right? So it's basically the probability of getting at most k successes in n trials, right? So for the binomial distribution, this is given as summation I is equal to 0 to k nci p into I into q into n minus I, like q raised to power n minus I, right? This is the cumulative distribution function, and if we calculate the expected value of the distribution, or basically the expected value of the distribution, we'll have basically np, and for the variance of the distribution or variance of the random variable, we basically have np into q, so npq. Right. So this is the, just a second, sorry. Yeah. So this is a binomial distribution. Then the second kind of distribution we talked about was for Poisson distribution. Okay. So when we are talking about the Poisson distribution, we are basically counting the number of events in a fixed interval of time. So number of events what is the probability of these many events happening in this much amount of time or any other thing. So what is the probability of finding uh, 10 dents in this much surface area of a car, right? If you want to uh, figure out questions like that, you use a Poisson distribution, right? And here the important thing, the things that we assume are that events are independent again, and basically that the uh, events happen at a constant rate, right? Constant average rate, actually, which is generally denoted by lambda, right? So an example of this would be the number of phone calls per minute to a call center, right? So we are looking at a fixed interval of time and we are trying to predict how many phone calls are happening in that particular interval of time. And therefore, this is a Poisson distributed variable, right? So here again, we have uh, P of x equal to k, which is equal to e raised by minus lambda into lambda raised by k divided by k factorial, where k is equal to 0, 1, 2, and so on and so forth. So this is basically tells us the probability of k events happening in a fixed interval, generally in terms of time, right? So probability of k events happening in a fixed interval of time, space, or something, right? And here again, we have the cumulative distribution function, which is f of x, which is basically given as probability that of x less than equal to k. So this is basically probability of at most k events happening in a fixed interval of time. Right. So this will again be summation of I equal to 0 to k e raised by minus lambda, lambda raised by I factorial. Right. And for the Poisson distribution, the expectation or the expected value of the random variable is equal to the variance, which is equal to lambda. Right. Next, we are talking about, next we talked about the normal distribution. So normal, or often called the Gaussian distribution. Right. In this distribution, so for example, what do you say? Most of the things that we talk about when the data is continuous and it is symmetric around a given value of the mean, right? Or when we have basically these bell-shaped curves, right? So if you have a curve which somewhat looks like this, right, where you have a bell kind of shape, where you have like a symmetric distribution around a center mean value. So that's when you use a normal or a Gaussian distribution. Some examples of this would be the distribution of uh, heights in a class, or test scores, and so on and so forth. Right. The important thing here is this is a continuous distribution. Right. So basically, here again, since this is a continuous distribution, we are given the probability density function, which is basically 1 by sigma into 2 pi to 2 pi all into e raised to the power minus x sigma square. Right. And here basically x belongs to minus infinity. Infinity. Yeah. For this, we have the cumulative distribution function, which is basically, which gives us the probability that x is less than equal to some given value x, which is basically phi of. So I talked about this phi function. Uh, in a way, this is like a z-score. So what we are doing here is basically we are subtracting mean and dividing by the standard deviation for our distribution of data so that we get a standard normal distribution, and then we can make the comparison. And there are basically tables which tell us what is the probability of x less than a certain value for a standard normal distribution. So we use basically those tables. So in one of the questions, we'll be doing that. So that time we'll take a look of how look at how this works. So in this case, the expected value is basically the mean mu, and the variance is basically sigma square. So here we have mu is the mean and sigma is the standard deviation in our distribution. Right. Then next, we also talked about the exponential distribution. And exponential distribution is basically uh, generally used to model the waiting time of a Poisson uh, distributed event. It's a Poisson process. Right. So what we are trying to predict here is basically we are trying to see what is the time until the next event occurs. In Poisson, what we wanted to see was what is the number of events in a fixed interval of time. But when we are looking at exponential distribution, we are looking at what is the time until the next event occurs. So again, if we are talking about uh, phone calls to a call center, so the number of calls in a given minute or a given hour will be Poisson distributed. So there's some average number of calls that happen per hour, and like we based on that, we can predict like what is the probability of getting 3 calls in the next 5 minutes or 10 calls in the next 5 minutes. But in an exponential distribution, what we are trying to look at is basically how long should the call center operator wait till the next call, right? So that is basically the exponential distribution. And when we are talking about the exponential distribution, so yeah, in the example, so example can be, what do you say? The one example is what I told you. The other one, as sir mentioned in the class, can be waiting time for bus at a bus stop. Right. Or another thing can be what is the lifetime of a battery. Right. So in this case, basically, the other important thing about exponential distribution is that it is memoryless, right? So, for example, if we are talking about the lifetime of a battery, and we know that the battery has run for 500 hours, let's say it's a very big battery that runs for a very long time. So, let's say it has run for 500 hours already. How, so what is the probability that it will run till 2000, like 7,000 hours, right? So, basically, if we are talking about that, so probability of running for 7,000 hours, given that it ran for 5,000 hours, in this case will actually be equal to probability of 7,000 minus 5,000, the probability of running for 2,000 hours. Right. So we would in a way think that this probability should depend on or should have something to do with the probability of this, but it does not. So that's why it's called memoryless. Right. So in this case, what we have is, again, it's a continuous distribution, a random variable, a continuous random variable. And so we have f of x equal to lambda e to the power minus lambda x, where x is greater than or equal to 0, and f of x, which is the cumulative distribution function, we have 1 minus e to the power minus lambda x. Again, x is greater than or equal to 0. Right. So here basically, what we are trying to get here is what is the probability of uh, waiting uh, till the next bus, right? In a way, that is what we are trying to model here. And the expected value for this is basically again equal to the, no, not exactly equal. So expected value is 1 by lambda, and the variance of this distribution is basically 1 by lambda square. And lambda is this parameter, right? So yeah, with that, we'll start with this week's practice assignment. Does anyone have any questions or doubt? Okay, great. Uh, so the first question is, what is variance of ax plus b equal to? Right. So according to the formulas of variance, if you guys remember, so variance of ax will be equal to a square into variance of x, right? Because a is multiplied here. And when we are talking about variance of b, which is a constant, the variance should be 0 because b is a constant and it does not vary. Right, there's no x here. So when we put this together, so variance of ax plus b will be equal to variance of ax plus variance of b, which is 0. So this equal to a square into variance of x. Right. So the answer here is option C, a square into variance of x. Right. The next question is, if f of x is given as this, or 0 is less than equal to x is less than equal to 2, what is the acceptance? So actually this should be expected value. Actually that or expectance also works, doesn't matter. So just a second. Yeah, so what is the expected value of this continuous variable, right? So what we are given here is basically we have this table here, which we should not have ideally, but yeah, it's for not for this question. So yeah, just it's confusing. Yeah, so we'll forget the table. So we are given f of x equal to 3/8 into 4x plus 2x squared for x in 0 to 2. Right. What is the expected value? So the expected value, the formula for the expected value, expectance or expected value here is x into f of x dx. So this is the formula of expectance or expected value for continuous distribution. So we multiply x into f of x and we take the integral of that. So if we are going to do this, we have x into f of x dx 0 to 2, because everywhere else it is 0, because we are not provided that information, right? We assume that everywhere else it's 0. So minus infinity to 0 will be 0, 2 to infinity will be 0. So we just have this interval 0 to 2, right? And then we have x into 3/8 4x plus 2x squared into dx integral from 0 to 2. If we take 3/8 out of this and we multiply x, so if we basically integrate this, we have our 4x square will become 4x cubed divided by 3, and our 2x cubed will become 2x to the power 4 divided by 4 in the limits of 2 to 0. So if we do this, two, and if we put 0 in place of x here, both of the terms will cancel out. Both of them will be 0. So we'll have 3/8 into 4 into 2 cube divided by 3 plus 2 raised by 4 divided by 2 minus 0 minus 0. 3/8 into 2 cube is 8. 8 into 4 by 3 plus 2 raised by 4 is, actually this will be 3. 2 raised by 3 is 8 again. So it's 3/8 into 32 plus 8 into 3 is 24 divided by 3. Go this way. 3/8 into 56/3, so 3 cancels out. So we have 7. So the answer here is option B, 7. Okay. So when we calculate the expected value for a continuous distribution or for a continuous function, what we do is x into f of x dx, the integral of that over minus infinity to infinity. So in this case, it turns out to be 7. Okay. Does anyone have any questions? Okay. So the next question is calculate the value of variance in an experiment of a single dice. Right. So this table that we have here actually should be here. So anyways, we'll make the table. We don't need the table. So the question is calculate the value of variance in an experiment of a single dice. So when we roll a single dice, what is the variance, right? So expected value and variance. So when we are rolling a single dice, let's say it's a random variable of x, it can take the values of 1, 2, 3, 4, 5, or 6, right? So we want to know what is the variance of x. Variance of x will be given by ex square minus ex whole square. Right. So we need expectation of x and expectation of x square. So first we need basically probability of x before we take the expectation. So since we are rolling a dice, everything is equally likely. We have 6 outcomes. So the probability of each of them will be 1 by 6. Right. Now the expected value is basically x into px, summation of that. Right. So we'll do x into px. So it's 1 by 6, 2 by 6, 3 by 6, 4 by 6, 5 by 6, and 6 by 6. And expectation of x will be basically the summation of all this. So this would be 1 plus 2, 3 plus 3, 6 plus 4, 10, 15, 21, 21 by 6. Yes. And again, we need expectation of x square. So that will basically be x square into p of x. This is again 1 square into 1 by 6, which is 1 by 6. 2 square, 4 into 1 by 6, which is 4 by 6. 9 by 6. 16 by 6, 25 by 6, and 36 by 6. Now, if we sum these up, we get expectation of x square, which is equal to 5, 14, 30, 55, 80, 91. So we have 91 by 6. Right. Now, to calculate the variance, what we do is expectation of x square, which is 91 by 6, minus expectation of x whole square, which is 21 by 6 whole square. This will be 91 by 6 minus 56. 91 into 6, 6, minus 54 by 46 by 6, 36 minus 451 by 36. 3. So if we do that on the calculator, it turns out to be around 2.917. So the answer here will be option C, 2.917. Okay. Next question is, what will be the expectation of a binomial random variable x with parameters m and p? So if we, so the parameters that we have here are m and p. M should be the number of, it can be either way. Yeah. So we actually do not need to fix which is what, but one of them will be the, when we say parameters for a binomial random variable, one of them is basically the number of trials that we are doing, and the other one is basically probability of success, right, in a given trial. So if we look at the formula for binomial distribution, the expectation is n into p. So one of them is basically our number of trials and the other is probability of success. So here again, the two parameters are m and p. So the answer here will be m into p. So option D. Right. Next question is the expectation and variance of a random variable X of a Poisson distribution is like how are they related? So we know in a Poisson distribution, the expectation is basically equal to lambda, and the variance of X is also equal to lambda. So in this case, the expectation is equal to the variance. So the answer will be option D. X. Next question is, what is the probability of observing no threes in 6 rolls of a die if the probabilities arise from a binomial distribution? Right. So we have to think of this in terms of a binomial distribution. We have rolls of die. So we are rolling the dice 6 times. So these are our independent trials or independent events. Right. In each of these trials, we should have a probability. So trial here will be rolling a die. Right. And the in each of these trials, we have a event called success. We have an event called failure. Since we are interested in observing no threes, so our success will be when no three in the row, and our failure is if there is a three in the row. Right. So the probability of success in this case, or P, will be equal to 5 by 6, since we have 5 numbers on the die that are not 6. So 1, 2, 4, 5, 6. And if any one of them come, we treat it as a success. But if 3 comes, we treat it as a failure. Right. So our probability of success in this case is 5 by 6. So probability of failure Q will be 1 minus P, which is 1 minus 5 by 6, which is 1 by 6. Right. And again, we are talking about 6 rolls of dice in total. So, just a second. So n here will be 6. And yeah, so that's all. That's what we can deduce from the question for now. So n is equal to 6, p is equal to 5 by 6, and q is 1 by 6. So what is the probability of observing no threes, right? So basically, if we have 6 successes, so in this case, we have defined our success as no 3 in the dice. So in 6 trials, if we get 6 successes, then only this will happen. If any one of them is 3, it does not happen, right? So now we have all our parameters and values. We'll look at basically, so the formula for the binomial distribution, probability of x is equal to k, is given as nck into p raised power k into q raised power n minus k. We have n is equal to 6 because we are rolling the dice 6 times. K is equal to 6 because in all of them we want no 3. So probability of success, which is no 3, is equal to 5 by 6. And the probability of failure is basically 1 by 6. When we get a Q. And when we get a 3. Right. So substituting those into this formula, probability of x equal to 6 is equal to 6c6. P is 5 by 6 raised to the power 6 into 1 by 6 raised to the power 0, sorry. This 6 minus 6, which is 0, which is equal to 66 is 6 factorial divided by 0 factorial into 6 factorial. So this cancels out. This is 1. Right. So into 5 by 6 raised to power 6 into 1 by 6 raised to power 0 is 1. Right. So if we do this, using a calculator, we have 5 raised per 6 is 15625. 6 raised per 6 is 46656. And this approximately comes out to be 0.3349. The answer here is option A, 0.3349. Right. Does anyone have any questions or doubts till now? Okay, great. So the next question is, the lifetime of a car battery is exponentially distributed with an average of 10,000 kilometers. If a person wishes to go on a trip of 5,000 kilometers, what is the chance that he or she will be able to do it without changing the battery? Okay, that's a blank side. Yeah. So here we are talking about the exponential distribution, and basically for it, the f of x is lambda e minus lambda x, and the cumulative distribution is 1 minus e is by minus lambda x, right? And the expected value is 1 by lambda. Right, all of that here. So f of x is basically equal to lambda e to the power minus lambda x. Right. Then f of x, which is the cumulative distribution, is 1 minus lambda e to the power minus lambda x. Expected value 1 by lambda, and variance basically 1 by lambda square. So we are basically, they're basically saying that the lifetime is exponentially distributed with the average of 10,000 kilometers. So the expected value of the average here is given as 10,000 kilometers, right? So that implies our lambda will be equal to 1 by 10,000. So if a person wishes to go on a trip for 5,000 kilometers, what is the chance that they'll be able to do it without changing the battery, right? So this f of x basically tells us what is the, what do you say? Right. Probability that x is less than equal to x. Right. So what is the probability that the x that we are getting? So the number of kilometers at which this thing will fail or the battery needs to be replaced is less than equal to x. Right. So probability of battery replacement below x kilometers. That is this probability, right? But what we want to know is basically what is the probability that the battery will not fail at 5,000. So what we want to know is what is P of x is greater than small x, right? So P of x is greater than x is nothing but 1 minus P of x is less than equal to x. And in this case, we know this is basically f of x, right? So we have f of x is 1 minus lambda e 1 minus lambda e raised by minus lambda x. So 1 minus 1 is 0. So this minus minus turns out to be plus. So we have, just a second. We have lambda e raised by minus lambda x. Right. So the probability that x is greater than small x is this. Now we are given that small x is equal to 5,000. So you don't want the vehicle to you don't want the battery to be replaced before 5,000, right? So probability that X is greater than 5,000 is nothing but lambda E minus lambda into 5,000. And we know that lambda is 1 by 10,000 from here, right? So I wrote down f of x wrong. There's no lambda here. Right. There's no lambda here. There's no lambda here. Not here. Right. So the answer is e raised power minus 5,000 divided by 10,000. E raised power minus 1 by 2. E raised power minus 0.5. The answer here will be option B, e raised power minus 0.5. Right. Now the next question is, suppose the test scores of 250 students are distributed so that the scores tend to cluster towards lower values with a long tail extending towards higher scores. What will be the probability distribution of the scores in this scenario? So what we know is basically scores tend to cluster towards the lower value. So this is, let's say, scores, and this is a frequency. Right. So more scores are around this value. Right. More points are around this value with a long tail extending towards higher scores. So we have a long tail like this. So the distribution looks somewhat like this. Right. Or actually can be somewhat like this. Doesn't matter. Like the shape you get it, it's like broad on the left hand side, and then it becomes longer on the right hand side, right? What would be the probability distribution? So it is not normal because a normal distribution looks like this. It's symmetric, right? It's not uniform because that also is uniform, looks like this. It's not geometric. It's actually skewed. And in this case, it is positively skewed because it has a longer tail towards the right hand side or towards the higher scores, right? So when we are talking about skew, when we basically say that something is positively skewed, that means more number of points are on the like on the right hand side or on the higher side. There are some points which are kind of like outliers, which are basically uh, taking the distribution that way. When we are talking about negative skew, it's the opposite. Right. Next question is, which of the following distribution is considered memoryless? So this is quite simple. Normal is not memoryless, uniform and geometric are not. Exponential is the one that is memoryless because probability that x is greater than s given that x is greater than t is actually equal to probability of x greater than. It does not depend on x greater than t. Right. The next question is, a fair coin is tossed 8 times. What is the probability of getting exactly 3 heads? Right. So we can, one way to do this would be to, actually we can't. So since there are 8 tosses, so in one of the earlier practice sessions, I think we did a question which was very similar to this, where, sorry. Okay, does anyone have any questions? Okay, yeah. So I think in one of the practice sessions before, we did a question like this, where basically we talked about a fair coin being tossed 3 times and what is the probability of getting 2 heads or something like that. So in that case, what we did was we wrote down all the possibilities since there were only 8 possibilities and tried to find a probability. But in this case, what we are going to do is we are going to use distributions because this is 8 times and it's not easy to list out all the different combinations, right? So again, when we are talking about a fair coin being tossed 8 times, this fits into the binomial distribution. Each of our toss will be an independent trial, which has a probability of success or failure, right? So in this case, since we are looking for heads, we'll say that probability of getting heads in a trial is our probability of success, right? So this P will be equal to 1 by 2, right? And again, Q is equal to 1 minus P, which is 1 minus 1 by 2, which is 1 by 2. Probability of failure is also half in each of these trials, right? So the next thing is we know that the coin is tossed n times, so n is equal to 8. 8 times, so n is equal to 8. And we are considered with the probability of getting exactly 3 heads. So out of n trials, what is the probability of getting 3 successes, right? So in this case, our k will be equal to 3. So what we want is probability of x equal to 3 or x equal to, yeah. So we know that probability of x equal to k in the case of binomial distribution is nck into p raised by k, q raised by n minus k. We'll just put that formula here. We have n is equal to 8, k is equal to 3, p is 1 by 2, raised by 3 into 1 by 2 raised by 8 minus 3. Right, so 8 factorial by 3 factorial into 5 factorial into 1 by 2 raised by 8. 8. So 8 minus 3 plus 3, it will become 8. Okay. So it will be 8 into 7 into 6 into 5 factorial divided by 3 into 2 into 5 factorial. This will cancel out. 3 into 2, 6 will cancel out. 1 by 2 raised by 8. So what we have is 8 into 7 divided by 2 raised by 8. So this will be 56 divided by 256. Approximately 0.218. Answer here will be option A, 0.218. Yeah. Now the next question is, if x is a normal random variable with mean is equal to 3 and variance is equal to 60, find probability of x is less than equal to 11. Sorry. Yeah. So we are given, okay. So we are given mu is equal to 3, sigma square or variance is equal to 16. That means sigma is equal to root 16, which is 4. Right. Now, what we are asked is basically what is the probability that x is less than equal to 11. Right. So what we can do in this case is we can convert our distribution. Since we are talking about a normal random variable, we can transform it to a standard normal distribution. So what we define is z is equal to x minus mu by sigma. So this is our new variable, which is a standard normal one. Right. So then the probability of x is less than equal to 11 will become probability of z less than equal to 11 minus mu by sigma. So this will become this, which is equal to probability of z is less than equal to 11 minus 3 by 4 equals to z less than equal to 2 minus 3 is 8, 8 by 4 is 2. Right. Now we have arrived at this. So probability that z is less than equal to 2. Now what we need to do is basically we need to, I'll just share my screen again. We need to look at something called a standard normal table. So can you guys see the screen? I'm assuming you, okay, thanks. So what we do here is, this is basically a standard normal table, which tells us in a standard normal distribution, which has a mean of 0 and a variance of 1, right? So what is this probability? The probability of the red area. So the probability of x less than equal to small x is the thing that is given in this table, right? So the highlighted area is shown here. So when we say what we want to find out is probability that z is less than equal to 2. So what we do here is on the left-hand side here, we go look for 2. And since we are looking for 2, the value here will be 2 and the first column 0.00. So the intersection of that, so the value here will be 0.9772. Can you guys see that? So that is basically the probability that x is less than equal to 2 or z is less than equal to 2. Now, if you want to figure out what is the probability that z is less than 1.96, right? So what you would do is you'll basically look at the row for 1.9 and then on top you will see 0.06. So this is the third digit. So 1.9, these are the first two digits. 0.06 is the third one. So you look at where they are intersecting. So this is basically the probability. So the probability that z is less than 1.96 is 0.975. So in our case, since we are looking at 2, the probability will be 0.9772. Is that clear? Okay. I'll just reshare my screen. So according to standard normal table, this turns out to be 0.9772. Right. So when you have questions like this, when you're talking about a normal random variable, it's generally easier to basically transform it into a standard normal distribution and then look up one of these standard normal distribution tables. So you'll find all of them online. And I'm not sure, but you will probably get some in the exam hall also. Right. Uh, Yeah, so this is how you can make these calculations. Make it easier instead of having to calculate using the formula for normal distribution, which is very complicated. Right. So the f of x, these formulas generally we don't use. So for the normal distribution questions, what we'll try to do is try to make it standard normal and then look at the value in a table. Right. Now the next question is, if the average number of calls received by a call center per minute is 3, right, what is the probability of receiving exactly 2 calls in a given minute? Right. It has already been noted here there is a Poisson distribution question, but uh, it's quite clear from the way the question is framed, because here we are talking about the average number of calls per minute per interval of time, right? So the number of events that are happening in a given fixed interval of time. So that is basically where we look at Poisson distribution. So here the question is basically that the average number of calls received by a call center per minute is 3. What is the probability of receiving exactly 2 calls in a given minute? So we are given that the mean or the expected value is basically 3. Now for Poisson distribution, the expected value is basically lambda. Right? So our lambda here is 3. And for a Poisson distribution, the probability of x equal to k is given as e raised per minus lambda into lambda raised per x, k actually, divided by k factorial. Right. So here k is equal to 2 because we want to calculate what is the probability of getting exactly 2 calls in a given minute. Right. So basically, is x is equal to 2 is given as e raised by minus lambda into lambda raised by square divided by 2 factorial. Right. So lambda we know is 3. We can substitute that e raised by minus 3 into 3 square divided by 2 factorial e raised by minus 3 into 9 divided by 2. It will be 9 into minus 3 will be equal to 0.0498. Divided by 2. You do this calculation. Into 9. So we get 0.224. Yes, right. So the next question is, the lifetime in hours of a bulb is exponentially distributed with a mean of 500 hours. What is the probability that a bulb lasts for more than 1000 hours? Right. So again, we are talking about exponential distributions. We have written down these formula here, right? F of x, capital F of x, then we also derive what is probability of x is greater than small x, e raised by minus lambda x, right? So probability of x is greater than a actually will be equal to e raised by minus lambda x. E raised by minus lambda k. In this case, the expected value of the exponential distribution is 1 by lambda, right? So in this case, which is given as the mean, which is 500 hours, lambda is equal to 1 by 500. Similarly, when we want to figure out probability that the bulb lasts greater than 1000 hours, so our k is equal to 1000. Have is e raised per minus lambda into 1000, e raised per minus 1000 divided by 500 is equal to e raised per minus 2. The answer here will be option A, e raised per minus 2. Right. Next question is, in a normal distribution, about 95% of observations lie within how many standard deviations from the mean? The answer here is straightforward, which is 2. So in a normal distribution, right, we have the mean at the center. We have within one standard deviation. We have talked about this before, right? So this is mu plus sigma, this is mu minus sigma. This area has 68% of the data. If we do 2 sigma, so this is mu minus 2 sigma, this is mu plus 2 sigma, then basically in this whole area, we have around 95% of the data. So this is 1 sigma, this is 2 sigma. And if we talk about 3 sigma, which is mu minus 3 sigma and mu plus 3 sigma, we in this area, we basically have 99% of the data almost. Right. So these are standard things that like are generally easy to remember. So like probably you might get a question from these. So like just keep in mind these values. Right. And the next question is, a random variable x has a binomial distribution with n is equal to 10 and p is equal to 6. So n is basically a number of trials, p is the probability of success, which is 0.6. What is the expected value, ex? So for a binomial distribution, we know that the expected value is n into p, which is 10 into 0.6, which is 6. Right. Which of the following is not a property of the normal distribution? So when we are talking about the normal distribution, we're talking about the bell curve, which looks somewhat like this. Right. So symmetric about the mean, this is true. So we have the mean here, and the distribution is symmetric about the mean. Mean is equal to median is equal to mode. That is also true because this is mean. Since this is the highest point, this is also the mode. And since this is also in the middle, this is also the median for a normal distribution. Also true. Area under curve is 1. This is also true because the area under the whole curve is equal to 1. Right? When we are talking about normal distribution, and we are talking about any distributions in relation to probability, always remember that the area under the curve should be equal to 1. Right? Because probability always sums up to 1. Skewed to the right. So this is false. This is not a property of the normal distribution because it is not skewed, it is symmetric. Right. Next question is, if the covariance between two variables, x and y is 0, it implies x and y are independent, x and y have no relationship, x and y are uncorrelated, and both B and C. So if the covariance between two variables is 0, that means they can be independent because we know that independent variables have covariance of 0. They don't covary, right? But actually, necessarily the opposite is not true, right? So if we get a value of 0, that does not mean that they are independent. If they are independent, we get a value of 0. But if the value that we get is 0, that means, yeah, that means we cannot say that if they're independent or not, right? Then the second thing is X and Y have no linear relationship, which is true because the covariance between them is 0, so they don't have a linear relationship. X and Y are uncorrelated. If we are talking about linear correlation, this is actually true. Right. So the answer will be option D, both B and C. Right. Just a second. Yeah. The answer will be option D, both B and C. The standard normal distribution have mean is equal to dash and variance equal to dash. We have talked about the standard normal distribution before. The standard normal distribution is a scaled version of the normal distribution, right? So when we have a normal distribution, we have the mean mu and the standard deviation sigma, right? For a normal distribution. But for a standard normal distribution, what we do is, let's say this is x. What we do is basically x minus mu by sigma. So now if you take the mean of this, the mean of this will turn out to be 0 because you're subtracting the mean. So you're centering the data around the mean, right? And the variance will be equal to 1 because we are dividing it by the variance. So the answer here will be 8, 0, and 1. Right. Question number 19 is the probability of observing no events in a Poisson distribution with rate parameter lambda is dash. So again, we go back to the Poisson distribution. We have probability of x equal to k, which is given as e raised by minus lambda into lambda raised by k divided by k factorial. Right. So rate parameter is given as lambda, so we'll let it be. And we want to have the probability of observing no events. So the k here will be 0. So probability that x equal to 0 is given as e raised by minus lambda into lambda raised by 0 divided by 0 factorial. We know that 0 factorial equal to 1 and lambda raised by 0 equal to 1. So what we have is e raised by minus lambda. The answer here is option C, e raised by minus lambda. Right. The next question is the exponential distribution is commonly used to model A, the number of successes in a fixed trials. That is not true because this is done by the binomial distribution. The waiting time between events, that is true because in an exponential distribution, we are looking at basically waiting times between uh, events that are occurring by a Poisson process in general. The distribution of test scores, this will be Gaussian or normal. And symmetric continuous data will not be modeled by exponential distribution because exponential distribution is not symmetric, right? So the answer here again will be B, waiting time between events. So that was all the questions we had for this week. Does anyone have any questions or doubts? Again, I'll just recap about the distribution because this is one of the most important parts of the course because you need to understand these distributions and where to use them. Otherwise, questions will come based on that mostly. Yeah. So you'll have most of the questions might have it already pointed out for you, like this is exponential distributed, Poisson distributed. But if not, you'll have to figure it out yourself. So in that case, you need to know how these distributions are, what they try to model, and so on. So I'll talk about it again. So when we are talking about the binomial distribution, uh, we are basically talking about having n trials, n independent trials. In each of these trials, we have two outcomes, which is success or failure. And the probability of success in each trial remains the same. So this P is same across trials. Great. So examples of this would be number of coin tosses or so n number of coin tosses, what is the output? How many heads we get in n tosses of a coin, or n rolls of a die, and how many threes, or how many even numbers, or how many numbers less than three, greater than four we get, and so on and so forth. So the probability that we get here is probability of getting k successes in n individual trials, which is given as this. The expectation is n into p, where n is number of trials and p is probability of success in a given trial, and variance is n into p into q, which is n is number of trials, p is number of probability of success in a given trial, q is probability of failure in a given trial, right? Now, again, in the Poisson distribution, we use the Poisson distribution when we talk about the number of events in a fixed interval of time, or actually a fixed interval of something. So if you go to Wikipedia and take a look, you will generally I think you will find that in the page of Poisson distribution, they have a photo showing the distribution of chewing gums on a street or a bench. Right. So that is also Poisson distributed because in that case, what you're looking at is the event is basically someone sticking a chewing gum, and the fixed interval where you're looking at is in terms of space. So the fixed surface area of the bench. Right. So similarly, in general, when we talk about Poisson distribution, we'll talk about a fixed interval of time. And again, for the Poisson distribution, the events are happening independently, right? And events can happen at a constant, events are happening at a constant average rate. So for example, here, the number of phone calls that we get per minute in a call center is something that would be Poisson distributed. Okay. Um, so here, the probability that we calculate is probability of k events happening in a fixed interval of time or space. Then next in the normal and the exponential distribution, both of these are continuous distributions. So normal distribution is applies to most things in nature where we expect data to be centered around a mean value, right, with some variance. So, for example, the distribution of heights of students in a class, or the distribution of weights, or the distribution of scores in a given exam. These all things are normally distributed, right? Uh, and yeah, the next one is exponential distribution. Another thing to remember for normal distribution is that for a normal distribution, the probability of a particular value is occurring is exactly is zero. The probability of x equal to 1 will be zero because the probability is calculated as a integral of fx dx. And if we put limits as c to c or 1 to 1, then this turns out to be zero, right? So for continuous distributions in general, the probability of a particular number occurring is zero, but the probability of a range is not zero. Right. Now the next thing is the exponential distribution, where we are basically looking at the waiting time of a Poisson process, or what we are trying to predict is time until the next event occurs, right? So, for example, you're waiting at a bus stop, you're trying to predict what is the probability of me waiting for 4 minutes for the bus, or me waiting for 5 minutes for the bus, or what is the probability of basically a battery going bad in 100 hours, or a bulb going bad in 100 hours, 1,000 hours, things like that. So this is again is a continuous distribution and it is memoryless. So basically the probability of a certain event happening because something has happened does not depend on that. You understand what I mean? We also talked about, now that I think about it, we also talked about uniform distribution, which I think I have not discussed here. Yes. We have also uniform distribution, right? Where basically we have a curve like this. So our uniform distribution is given as f of x is equal to, this is again a continuous distribution where f of x is equal to 1 by beta minus alpha in the range of this. So the probability of anything happening is the same, right? Any particular, what do you say? Any value between these, the probability of that happening would be the same. So that is a uniform distribution. So the probabilities are uniformly distributed across all the values. But again, exactly the probability of one particular value occurring here will be zero because this again will be an integral. So when we talk about this, again, we talk about a small range here, right? Yeah, so the uniform distribution generally rarely comes up in nature, but yeah, when we talk about something that is, what do you say, that has a large number of continuous outcomes and the probability of each of them happening is around the same, we are talking about a uniform distribution, right? If we basically, we defined it as a continuous uniform distribution, it can also be defined discretely. So if we talk about a discrete uniform distribution, we'll talk about rolling a die because all of the outcomes, so basically we have a discrete random variable which can take the form 1, 2, 3, 4, 5, 6, and all of them are equally likely. So that is uniformly distributed, right? Discrete uniform distribution. But if we talk about continuous uniform distribution, for example, if I ask you guys to pick a number between, pick a minute between, pick a time between now and 8 o'clock, right? So you're all probably equally likely to pick, you're probably equally likely to pick any particular time, right? That's why it's a uniform distribution. So generally, if you have questions, try to see if like you have things like if all the outcomes are equally likely, or if all the events are equally um, hmm, likely to happen, and like look for things like that. And there, these places you'll probably be using uniform distribution. Right. So does anyone have any questions or doubts? I don't think you will be asked any derivations of any of the distributions, but you need to understand how they work and what formulas to use, how to get at their expectations and variances. From what I understand, the exam will be MCQ questions only. So you won't have to derive anything, but you need to make calculations. But just in case I am not right, please ask these questions in the discussion forum also of the course. Uh, because yeah, the TAs there know more about the exam and the exam pattern and yeah, things like that. So it'll be better if you ask it there. Thanks. So moment generating function. What do you say? So for wait, just a second. Yeah, so you will be given a scientific calculator, which I think works online, which will be there in your computer system where you are giving the exam. Right. So, how do I say this? Instead of working or looking at, uh, what do you say, the probability density function or the probability mass function or the cumulative distribution functions that we talked about, right? So when we started for each of these distributions, we had a uh, cumulative distribution function f of x, right? Which we used to solve many of the questions, especially for the exponential distribution, right? So in moment generating function is basically another way of looking at random variables and their probability distribution, right? So uh, basically for random variable, for example, let's say we have a random variable x. So the moment generating function of x, right, is defined as something like this, which is equal to, sorry, it's not summation. It's basically expectation of e raised by t into x, right? So this is basically called the uh, moment generating function. So in simple words, you take the random variable, which is a random variable x, right? For any random variable x, we have a corresponding moment generating function, which is always defined in this terms, right? So your x can be a random variable, which is Poisson distributed, which is exponential distributed, which is normally distributed, but all of them will have moment generating functions, which are of these forms, where the x here can vary. So for the normal distribution, you'll input x is equal to f of x here, which is 1 by 2 sigma 1 by sigma into root 2 pi, that formula. Or for exponential distribution, you can enter the e raised per lambda, that formula, right? Uh, Basically, what it allows us to do is that, what do you say? It can help us when we talked about data, we talked about moments, right? Moment of the data. And you remember that's one of the way in which we arrived at the mean and the variance of the data based on moments, right? So this basically does the same thing for a distribution, right? So what do you say? When we have a moment generating function for any like discrete function, what we'll have is uh, basically summation of e raised by the xi into pi, right? I is equal to what, 0 to infinity, right? And for continuous probability density function, the moment will basically be e raised by t into x, uh, f of x dx, integral from minus infinity to infinity, right? So I think in the normal class for normal distribution, what Sir basically showed is that uh, so basically where this comes into use is when we have a very complicated distribution, right? So for example, if you look at these, the binomial distribution is not that complicated. The formula that we have is quite straightforward. For the Poisson distribution, again, the formula that we have is also very straightforward, right? But for the normal or Gaussian distribution, the formula that we have here is very complex. So using that formula to get at basically the mean or the standard deviation is slightly difficult. So what we do is basically we use a moment generating function, which basically helps us get at the expected value or the variance of the data. Is that clear? So for example, when you basically take the derivative of this, right? So you basically, for any function, you can make this, what is it? Uh, Basically, in this formula, for any distribution, you have to just input the value of x, right? And then you get a term here. Now, if you differentiate that term one time, basically, you will get another term, right? And if you differentiate it twice, you will get a second term. And basically, if in this differentiation, you basically input instead of t, you put 0. And here again, instead of t, you put 0. What you get here is basically the expectation of x. What you get here is expectation of square. So since variance is calculated as expectation of x square minus expectation of x, you can basically, for any given distribution, however complicated the formula, you can just take the derivative twice and evaluate it at 0, and then use that to calculate the variance of the distribution. Right. This is basically the main function of using a moment generating function. It is always of this firm expectation of e raised by t into x, where x is our random variable, right? And then when we take the derivatives and evaluate it at 0, we get the expectation of x and the expectation of x squared. So this basically gives us the mean of the distribution. And to calculate the variance, we can just subtract, make this calculation ex squared minus ex whole square. Right. So an easy way to get at the mean and the variance of a distribution is using the moment generating function. Is that okay? Okay. Does anyone else have any other question? I'll be here till 7:45, which is around 10 minutes. If you guys have any questions, feel free to unmute yourselves or ask in the chat box. And just turn off my camera for a few minutes. I'll just check once if there are any suggested books for the course. Right. Okay, so actually, if you go to the uh, tab in what do you say in NPTEL, if you for solving questions, is it? Sorry. So there's this book called Biostatistical Analysis by Gerald H. Zar. Just write it out on the chat. So I don't think it has a lot of problems. It's one of the books that we uh, generally follow. Uh, it has some questions, but I don't think it has a lot of questions. Another one would be, I think, Fundamentals of Biostatistics by Rosner. You can check these out. You should also ask this question on the discussion forum. I can't find anything for the course, but I think there'll be some recommended uh, books for the course also, which would probably have uh, some questions that are aligned more towards the uh, course, right? Like, so they talk mostly about the. Okay, actually, I found it. So I think these two books follow. So these were basically books that are suggested by the professor. I think if you go through these books, you'll get more problems to solve, which are similar to the ones covered in the course. Right. So if no one has any more questions, we'll stop here. So I'll upload the videos for this week and next week today. Yeah, sorry for not uploading it last week. Okay, does anyone have any more questions?
Sir, I have a
Yeah, yes.
request.
Yeah, yeah.
Could you kindly upload the session 4 problem solving sessions with that one at
Yeah,
top?
yeah, yeah. Yeah, I'll upload both of them, session 4 and session 5, which is today.
Okay.
I'll upload both of them by tonight.
Oh,
Yeah.
thanks.
Okay, so we'll stop here. We'll meet again next week. Uh, I'll upload both of them. And thanks for attending. I'll see you again next week where we discuss the next week's lecture. So probably next week's class might not be on Friday. As I'm traveling. I have requested to shift the class. So we might have the class on Monday. Just informing, like just in case it happens. Yeah. Monday evening. Okay. Okay. So thanks. I'll meet you guys next week. And yeah, bye.